All right. Good morning. Um, any question before we start? If you have any question about the homework problem, you can ask me to work on any of homework problem. So, all right. We are on chapter 4. We are talking about uniform series of payments. Then we have a repeated cash flow. If it starts from year 1 and it goes all the way to year end, we call this uniform series of the payments. So we can find equivalence of this cash flow diagram. Either we can find what would be the future value which is equivalent to this series of the payment. So then you can replace this one with the original cash flow diagram. Or you might say, I would like to know what would be the equivalence of this cash flow diagram at present time. So then you can replace this with this one. So for if A is given and you would like to find F, you can use this equation. F is going to be A times F over A. A is given, we are looking for F at the interest rate of I over n periods of time. A times F over A I n, and this is the equation. If you like to use the equation, it's going to be so we call this uniform series compound amount formula. But you can say if F is given, I would like to find what would be the A which is equivalent to that. Just inverse this and say A would be F times inverse this. F is given, we are looking for I. We are looking for A at the interest rate of I and over n periods of time. We call it uniform series sinking fund formula. Just inverse this. A would be F times I 1 plus I over n minus 1. Or you might say I'm looking for P when A is given. So P would be A times A is given, so P over A I n, and the equation for that is this one. And we call this uniform series present force factor or formula because it's going to give us the present force or the present value of uniform series of the payment. Or if P is given, you are looking for A, just inverse this one. A would be P times I 1 plus I over n 1 plus I power n minus 1. And here you are looking for A. When P is given, just inverse this. And we call this uniform series capital recovery formula. We call them factor inside the bracket. The equation is called formula. Is that yeah? Good? All right. So we are introducing the standard forms of the payment. We started with the single payments. Now we talked about the uniform series of the payment, but in reality, you might have some cash flow diagram which they are different than these standard forms. So your task is working on those cash flow diagrams to change it to this standard form and find the present value, future value, or any other terms that you are looking for. So this standard form is going to help us to do the calculation easier. So let's work on this example. There is an investment project which says it's gonna pay you $140 every month for 5 years. So you get paid. You get paid every month $140. From month 1, $140. You get paid month 2, $140. And since it's gonna continue for 5 years, which is 60 months, the cash flow diagram for the receipt of the money is gonna look like this. So this investment project says if you want to get 140 every month for 60 for 5 years, you should pay $6,800 at present time. So if you pay $6,800, you can receive $140 every month for 5 years. Now, if you know that there is another project which can give you 1% interest per month, or we are saying that if your desired interest rate is 1% per month, the question is, are you gonna reject this investment project, or you are gonna accept this, or are you gonna pay $6,800 and in return get paid $140, or you are gonna invest your money in the other project which is gonna pay you 1% per month? Clear? So we want to decide about this. So interest rate 1% per month. Now, if I just look at the benefits, 0, 1, 2 to 6, 140, 140, all the way to 140. If I find its present value with this interest rate at present time, so if I find P which is equivalent to the benefits that I'm gonna get paid over the next 5 years, then I can compare this P with the money that I have paid at present time. If P is greater than the money that you are gonna pay, then we accept the investment project. But if P is less than 6,800, we reject. Make sense? Alright, so to do that, we are given with A, we are looking for P. We are looking for P when A is given. So P would be A times P over A. I is 1% per period of time, which is month. Number of periods is 60. A is 140 times so this is 1%, this is 60. We are looking for P over A. We are looking for P when A is given, 44.955. 0.95. Or you can calculate by uh, $62, 30, 93.7. So the money that you receive, it's gonna worth $62.93.70 at present time. But you are gonna pay for this benefit $6,800, which means you shouldn't accept this investment project. Make sense? Any question about this? Make sure that you know the steps and the logic behind this problem, because we are going to go to the advanced example and I'm going to ask you to work on. Alright, now if I want to make this investment more attractive, should I increase my desired interest or should I decrease my desired interest? So if I change my desired return to 2%, for example, am I gonna get this more attractive than before? Or if I assume I equals to 0.5%, it's gonna be more attractive than now. Everybody can see what I'm looking for. Any volunteer?
You want the interest rate to be increased.
Increase. So by increasing this, we can make this more attractive. This is what you're saying. Okay? Any different thoughts? suppose interest rate is 0, okay? If interest rate 0 means money doesn't have any time value. So all values, they have the same, all payments, they have the same value. So I can add them up. 60 times 140. It's gonna be $8,400. True?
Yep.
So $8,400 versus $6,800. So you prefer to get that. So you prefer to get $140 every month for 60 if your desired interest rate is 0. By increasing your desired interest rate, you are gonna discount the future payments. So by increasing this, we discount the future payments heavier than before. Everybody can see that. This is how the interest working. But you prefer today money than future money because we have interest rate. So by using the interest rate, you are going to discount the future payments than before. So now back to this problem. Our benefit is 62.93. If I want to make it more attractive, I want to increase it. So I should discount it less heavier than before. It means I should decrease I from 1% to something less than 1%. Is this any question about this? So again, at the interest rate of 0, which means we don't have any preference between the timing of the money, different timing of the money, you can add them up, you will get 8,400. By increasing the I, this 8,400 is gonna decrease. By increasing the I, we are gonna discount the future payments. So if you look at this, do you want to increase this or decrease? You want to increase this to make it something, some value close to 6,800. So then you need to decrease the I to make it possible. All right, now the question is the same example, but you want to know what should be the monthly interest rate to make this equals to 6,800, or you accept the offer. So the question is what should be the I that we accept the offer. So what is the monthly rate of return? So it means the present value, which is A times P over A I 60 should be equal to 6,800. A is 140. So then this factor is should be equal to 6,800 divided by 140. Which is 48.57. P over A, I 60 should be 48.57. It means the interest rate which makes this factor equals to 48.57 is gonna make this investment desirable. So you are gonna accept, at least you have no preference between 6800 or future payment. You have two ways. Either this is the factor that we are looking for. Plug in n equals to 60 and solve for I, which is difficult to solve this problem. Or look at the tables on the appendix C. For n equals to 60, find two interests which they provide this factor on both sides of this factor. So this is 48.57. If you look at 0.5% at n equals to 60, P over A is 51. So $51.72, and when we change it to 0.75%, P over A I60 is gonna be this 48.174 for 0.75%. The value that the I that you are looking for has this 48.57. 48.57 is between these two. At I, this factor it should be 48.57. So next step is finding two I's which they are on both sides of your desired factor. So your desired factor is 48.51. At 0.5% it's going to be 51, at 0.75% it's going to be 48.174. So now we are going to use the linear interpolation. This is how we are going to use it. So draw this axis representing the I. This axis is representing P over A, I60. So at I equals to 0.5, this factor is 51.72. Suppose it's going to be somewhere here. At 0.75, the P over A is 48.174. These two. And your desired P over A is 48.57, somewhere here. Connect these two, it's going to give you a line. You are looking for this I. This I has the value of 48.57, which is the interest rate that you are looking for. Good? Now the rest is just simple linear interpolation. A, B, C, D, E, and F. So if you look at this triangle ABC, ABC, the tangent of this angle is AB alpha. Tangent of alpha is AB dividing by AC. AB dividing by AC. What is the AB? AB is 51.72 minus 48. I'm looking for AB. AB is going to be this minus this. Dividing by AC. AC is 0.75 minus 0.5. So keep this. We are going to use this. Now look at this triangle. VFE. Triangle VFE. This angle also has the value of alpha. These two are the same because these two parallel, this line is crossing them. So this angle is equal to this angle. The tangent of this angle is BF dividing by FE. BF is going to be 51.72 minus your desired value, which is 48. And here EF is I, whatever is that, minus 0.5. I minus 0.5. Now, the tangent of alpha equals to each other. Set this equals to this one and solve for I. So let me $51.72 minus 48.174. This is going to be 3.546. And 0.75 minus 0.5% is going to be 0.25. And here 48 minus 50.57, 3.15. Dividing by I minus 0.5. Just set these two equals to each other. 3.546 dividing by 0.25 equals to 3.15 dividing by I minus 0.5. This multiplied by this equals to this multiplied by this. I minus 0.5 times 3.546 equals to 3.15 times 0.25. Then this dividing by this. I minus 0.5 equals to 3.15 times 0.25 dividing by this. And if you are looking for I, move 0.5 to the other side. So 3.15 times 0.25 dividing by 3.546 plus 0.7221. So by linear interpolation, the interest rate which makes 6,800 equals to the future payments should be 0.7221. Or you can say the rate of return for this investment is 0.7221. Or this investment is going to pay you 0.7221%. Everybody, if you have any question about linear interpolation, you can ask. because some homework problem and in exam you might see something like that. So I expect you know how to find that. If you could find this value in the table, you are lucky and you can go for that. But if you just find the value between two other value, then you have to do linear interpolation. Good? All right. Let's move to this example. And we are gonna work on some example to show you how you can use this equation to solve the problem. So suppose one student is borrowing $100 per year for 3 years, but the loan should be paid back at 2 years after the last payment. So, and the bank or the loan is going to charge the student by 15%. The question is how much the student should pay after at the end of 5th year. So for the first 3 years, it gets paid $100. We would like to know what would be the equivalence value of this cash flow diagram at year 5, or how much a student should pay at year 5. So this is a uniform series of the payment. If you use F for a given A, the value that you will get is gonna be N is 3, 0, 1, 2, 3. We have 3 payments. If you use this, the value that you will get is gonna be at year 3. But you are looking for year 5. So what you can do is, you have one single payment here, which is F1. Now find its equivalence at year 5. So it's going to be F equals to, this one is present value, which has 2 years distance from year 5. So it's going to be F1 times P over F over A, P over F over P, interest rate of 15, and N equals to 2. So then this F value, it's gonna give you the amount of money that the student should pay back at the end of 5th year. So as you see, this cash flow diagram is kind of uniform series of the payment, but it's not looking for the future value at the end of 3rd year. It's looking for the future value at the end of 5th year. So what we did, we just used this equation to find equivalent future value at the 3rd year. Then we move this to the 5th year to find the F. Or you can break this another. This method is always working, but it may need more calculation. Just break this to 3. to 3 cash flow diagram with $100 payment. And then you are looking for future value at the year of 5. Find its value at the year of 5 and label this as a F1. You know how to find that? F1 would be present value times, we are looking for F when P is given, interest rate is 15%, and N is 1 year, 2 year, 3 year, and 4 year. Find F2 for this. Everything is gonna be the same except the number of periods. 4 is gonna change to 3. 1 year, 2 year, and 3 year. And for this one, to not find F3, with 2 years distance from future and add them up. And these are the numbers if you read from the book or if you use the equation. You should get the same result. This is solution 1. I just break the cash flow diagram to 3. I could find future value for each, and then I add them up, and I could find F. Or I used this equation to find its future value at year 3. Then I moved it to the year 5. By multiplying 347 times F over P 15% 2. F over P 15% 2, and F1 is $347. Good?
On a test, would you want us more to use the tables or the equations?
Sometimes I don't provide the tables, and I'm saying that, okay, use the equation. So if you are given with the table, you can use. But if you have option, whatever, it's easier for you, which I think tables would be much easier. So you solved one problem on the homeworks, which was you were given. It was, I think, the last problem on homework 3, I guess. You were given with the maintenance cost over the time that you need to withdraw that money over the future years, and the question was how much the maintenance cost is gonna worth at present time. Or we can say how much you should set aside at present time to be able to withdraw the maintenance costs in future years. So this is something like that example. So we need to withdraw $20 on second year, $30 on third year, and $20 on fourth year. Now the question is how much should we set aside in the account which pays you 15%? So 0, 1, 2, 3, 4. $20 you want to withdraw, $30 and $20. The question is how much should we deposit to the account which pays you 15% interest to be able to withdraw this. If the interest rate was 0, you could say 20 plus 30, 50 plus 20, 70. If you just put $70 with no interest, you can withdraw $20, $30, and 20. But the money has time value, so you can deposit less to get benefit of the interest. So we are looking for the present value of these 3 for this cash flow diagram. When you look at this problem, you can at the beginning, you don't see any standard forms of the payment. It's not uniform series of the payment. You can solve this in different ways. Like the previous problem, just break this to 3 single payments, $20. What would be its present value? You can find present value of this by future value, which is 20, times P over F. I is 15% and N is 1, plus 0, 1, 2, 3, 4. The second, sorry, it's occurred at year 2. Second, it occurred at year 3, which is $30. Find P2, which is F2, which is 30 times P over F. I is 15%, N is 3. And last one is $20. Similarly, find P3. And then add them up. This is one way that you can do. Second solution, just break the cash flow diagram to these 3. Find the future value first. Find the future value of 20 at F1. F1 would be P, which is 20, times, we are looking for F. When P is given, interest rate is 15%, 1 year, 2 years. 2 years this time. Do the same things for F2 and same things for F3. Add them up, get F. Now you have F, which occurs at year 4. You have F, which occurs at year 4. Find its present value at time 0. Another way that you can treat this, just break this cash flow diagram 1, 2, 3, 4 to some $20. Year 3 has 30, so you add $10 here. Then, if you look at this is the uniform series of the payment, but it's starting at year 2. It should start at year 1 if it wants to be uniform series of the payment. But to make it similar to uniform series of the payment, just set a year number of 1 to this, year number 2 to this, and year number 3 to this, and this is going to be year number 0. So 0, 1, 2, 3. Now, if you look at 0, 1, 2, 3, it's a uniform series of the payment. If you are looking for P, P1 would be A times P over A. Interest rate is 15%. Number of years is 1, 2, 3. The value that you will get here, it's going to occur at time 0 of this, which is P1. Then move this P1 to the present time. P1 times, we are looking for P when F is given, I is 15%, N is 1. So you can find P prime. Move this $10 to the present time. One, 2, 3, and add these 2. So we find P1 by multiplying 20 by P over A, 15% 3 years, and then move it to the first year because it has 1 year distance from that, and then add $10 also to that to get $46.28. So I just wanted to show you by given cash flow diagram you can change it to different standard forms of the payment and work with those cash flow diagrams. All right, let's look at some relationship between these components that we derive. F over P I N is going to be 1 over P F I N. You remember F over P I N is going to be 1 plus I power N. P is given. You are looking for F. What would be the F? F would be P times F over P I N, or P times 1 plus I power N, which is this. If F is given and we are looking for P, it's going to be F times 1 plus I power negative F. So as you see, this is going to be 1 over P over F I N. So it's for uniform series of payment also it's valid. A over P I N is going to be equal to P over A I N, and F over A I N is going to be equal to 1 over A over F I N. Similar things. I'm gonna talk about these three relationships which are important on Monday class, and I will collect them.